Okay, let's talk about vertical transformations of a function. So, when we multiply a function f of x by a constant a, then you get a new function h of x as a multiplied by f of x. So, this causes vertical change in the graph of f of x, a vertical change in this graph depending on the value of a. So if the absolute value of a is greater than 1, the graph f of x is vertically stretched. If the absolute value of a is greater than 1, then the function f of x is vertically stretched. This means it pulls away from the x-axis. The graph becomes more steeper. On the other hand, if the a is in between 0 and 1, the graph is vertically compressed. It moves closer to the x-axis. The graph becomes flatter. So in both cases, the basic shape of the graph remains the same, but the height of each point will be scaled according to this a. So that is how vertical stretching and compression will work. So we'll see some examples next to see how this works. Okay, so let's begin with the basic function f of x equals x squared. So this is our parent function, a simple upward opening parabola. So now what will happen to this function if we multiply this by a constant? So let's define g of x as 2x squared. So g of x as 2x squared. So here we have multiplied f of x by a constant 2. So this is a vertical stretch. Because here the constant is greater than 2. So this is going to be a vertical stretch of the graph by a factor of absolute value of 2. By a factor absolute value of 2. So in simple terms, the graph becomes much narrower because all the y values are doubled. So here each point on the graph is pulled further away from the x-axis. So let me sketch this. So remember, this is narrower than the parent function. So this is your g of x. Now let's take a look at the third function h of x. So h of x is half multiplied by the x squared. So again you have multiplied the parent function by a factor half. So half is in between 0 and 1, which means this is a vertical compression. This is vertically compressed by a factor of half. So this causes the graph becomes much wider. All the y values are scaled down by half. So they are pulled close. Okay, so let me sketch that. So it's going to be something like this. Well, so now you have all the three functions in the same coordinate system. So now you can observe their shapes and you can compare them. So this visual representation will help you to reinforce how the vertical stretch and compressions affect the graph. So now let's take another example. So here in this example, let's take the parent function as x. y equals x. So this is a straight line passes through the origin with a slope 1 and it rises at a steady 45-degree angle. So now let's apply some vertical transformations. Okay, so here let's take g of x as 3 multiplied by x. So here we are multiplying f of x by a constant 3. So since 3 is greater than 1, so this is going to be a vertical stretch. This is vertical stretch. Let me write this. So the vertical stretch will be by a factor absolute value 3. So that means the line still passes through the origin, but it rises much more steeply. The slope is now 3. So the slope is now 3. So the line will be something like this, a line which passes through the origin, but it is much steeper than f of x. So this is your g of x, which is 3x. Okay, so now let's take the other function, which is h of x. So here I have taken h of x as half multiplied by x. So this time we are multiplying f of x by half. So this is compressed. So this is going to be a compression, a vertical compression. By a factor half. Okay, you have to have absolute values. Okay, so over here, the line becomes flatter because it rises more slowly. So on this line, the slope becomes half. So if you sketch this, it's going to be something like this. So this line is much closer to the x-axis. It's something like this. So remember here g of x which is equals to 3x is vertically stretched. So this is the steeper line. On the other hand, h of x is a vertical compression. So it is the flatter line. So all these graphs will pass through the origin, but the steepness of the lines will change with the value of the multiplier. Next example. Okay, so now let's try to sketch this function. So this is a quadratic function, so we can analyze it by comparing with the parent function. Let's take this parent function as x squared. So I'm going to name the change of I'm going to change the name of this function. It's because here I have already taken f of x, so I'm going to name the parent function as y equals x squared. So the first step would be to construct, let's say, 2x squared. So we have to construct 2x squared from the parent function because 2x squared is a term of f of x. So here you can clearly see this is going to be a vertical stretch because you have here a constant. So the constant is greater than 1, I'm sorry. So this is a vertical stretch. So this makes the parabola much narrower than the basic y equals x squared graph. So each y value grows twice as fast as the parent function. So this will become something like this. So this is your g of x. So this is 2x squared. Okay, so now you have to transform, like you have to get 2x squared plus 1 from this function. So the plus 1 at the end shift the graph up by 1 unit, which means the vertex of this parabola, instead of being at the origin, now it's going to move into point. The x value is going to be 0 and the y value is going to be 1. So now let's shift this graph upward by 1 unit. So let's say it's over here. So this point is going to be 1. So remember, so this red line over here will represent f of x. Okay, so remember this is a parabola, but it is much narrower and it's opened upward and it shifts 1 unit up from the origin.